Okie dokie. Yeah, you were not here, Drake. Chapter 10 has us talking about gases. So, obviously, we are getting back into some math part of chemistry. But I actually really like this chapter because it's pretty applicable to, kind of everyday stuff, but also the math portion of it. It's really, a lot of it's just plug and play, meaning there's formulas involved. And the other one is the conversions are pretty set and standard. Okay. So, talking about gases. Gases can obviously have very different properties. Just like elements on the periodic table all have very unique properties associated with them. Gases are unique in their way. If we look at oxygen and nitrogen, okay, oxygen sustains life. Nitrogen does not in terms of humans. Okay, plant life obviously really like nitrogen, but for us, we utilize oxygen to help us breathe. Now, what's interesting about that is the atmosphere. Does anybody know what the atmospheric makeup is of gases? The atmosphere is made up of about 78% nitrogen and only 21% oxygen, and the remaining percent or whatever is just a hodgepodge of various gases. And so, even though the atmosphere is made up of 3/4 of a gas that we cannot utilize personally, we're still able to utilize oxygen to help sustain. Now, gases and liquids are both considered fluids. However, there are differences between them. And when we say fluids, that just means that the molecules can move around each other. And so gases expand to fill their containers, are highly compressible, and have extremely low densities because of the volume that they make up compared to their mass, results in their densities being very tiny. Now, when we try to mix liquids and gases, again, we get different results. When we get two different gases or more gases together, we form homogeneous mixtures, no matter what their identities or proportions of the gases are. If you look at liquids, if we try to mix two different types of liquids together, for instance, water and gasoline, they do not mix. They form heterogeneous mixtures. But above every liquid, especially at room temperature, there's always going to be some vapor of that particular liquid. So even though gasoline and water liquids cannot mix to form a homogeneous mixture, the vapors from gasoline and water can mix to form homogeneous gas mixtures. That's because of their relative distances between each other. Gases have a very far distance when we speak about the three different states of matter. And so the molecules of each of these vapors is allowed to kind of sneak in without having to interact really with a lot of the other vapor molecules. So gases are unique. Okay, gases are important. Gases can be utilized for our benefit. So that's why it's a neat little chapter here. Now, we're going to start off talking about pressure associated with gases. Okay, we experience atmospheric pressure on our bodies at all times. And we can calculate pressure, which is the amount of force applied to an area, by simply taking the force applied by the gas divided by the area over which it is applied to. Now, if we think about atmospheric pressure, we think about it as a column of air. Okay, there are columns of air all around us. And since air has mass, that column of air is constantly pushing down on us. Okay? So imagine if we're at sea level. Again, just pretend this is the sea. We're at sea level. We have this entire column of air bearing down on us. Well, let's say we go to the Rocky Mountains. Everyone know what the Rocky Mountains are? Just making sure you never know. You actually are very much higher in elevation. So as you go higher in elevation, imagine what it does to that column of air that's bearing down you. It reduces it. So we have a reduction of pressure on us at higher altitudes, which is one of the reasons why, if you do go at higher altitudes, it's a little more difficult to breathe. And it's also different when you try to cook food. The lower the atmospheric pressure, or therefore the higher the altitude you are, the lower the temperature that water will boil. But even though the water is boiling, it's still boiling at a lower temperature. So oftentimes your cooking time has to be adjusted for that reason. So gas affects our lives more than just breathing. It affects how food's made. It affects how other chemical properties act. So let's talk about units of pressure that we are going to talk about throughout this chapter. The first is the Pascal. Okay? Where 1 Pascal is equal to 1 Newton per meter squared. Now, I have a slide on here that is going to give you a complete summary of all these pressure units. Okay? And these are what our conversion factors are going to be. Okay? So we've got Pascal, we've got bar, we have millimeters of mercury, or what we also call torr, T-O-R-R. And so torr is a 1-to-1 ratio with millimeters of mercury. That's because Evangelista Torricelli was an Italian mathematician and physicist who basically pioneered and dedicated his studies to the idea of a barometer. Where do we use a barometer? In what aspect do we typically hear about barometer? Does no one in here watch the Weather Channel as often as I do? Okay, I'm old. Have you heard of barometric pressure? Okay, you kids need to learn to watch the weather because we're in the Midwest. Okay. The barometer measures barometric pressure or atmospheric pressure. It is often used to help us predict weather activities, weather patterns. When you start seeing significant fluctuations in barometric pressure, you can almost guarantee that some sort of weather system is moving in. Now, when we talk about millimeters of mercury or torr, either one's kind of interchangeable. These are literally the difference in heights measured in millimeters between 2 connected columns of mercury. Okay? 1 atmosphere is what we typically use to measure atmospheric pressure, at least we do, is equal to 760 torr. Or if you want to add this little addition to this statement, so you can write also in there 760 millimeters of mercury, mmHg. So you're going to have about 5 or 6 units of pressure that we're going to be utilizing throughout this chapter. And here are your conversion factors. Okay? Everything you see on here is equal to everything else. So 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr, or 1.01325 times 10 to the 5th pascals, or 101.325 kilopascals, or even 1.01325 bar. Now, the last 3 numbers, what do you notice about them? Listen, what do you know about those last three numbers? What's that? They all have 325 and 101. They all have the same 6 numbers with slight variations. Okay? Mainly the decimal point, and with pascals, the 10 to the 5th power. Okay? So, if you are going from one of these units and converting to these units, these are the conversion values that you're going to use. Okay? So let's take a look at how we convert some of these. Okay? So if we have 0.357 torr, maybe I'll get there eventually. Can you even see that back there? Yeah? Okay. So if you're watching this at home, I'm looking, follow my mouse, I'm doing this one right here. So if we have 0.357 torr, we need to convert this to, oh wait, hold on. Sorry. That's what we're converting to. 3.357 atmospheres. Okay. And so if you recall from way back when we did dimensional analysis and conversions, what we know or what we're given always is listed first. And so if I want to go from atmospheres to torrs, I go to the previous slide. Okay. Where I have 1 atmosphere is equal to 760 torr. And so, who goes where here? Where does torr go? Where does atmosphere go? If I need to have torr in my answer. Torr goes on top. Very good. Torr goes on the top. And atmosphere goes on the bottom. That way, these can cancel out. And so here, then you put your conversion factor. There's 760 torr is equal to 1 atmosphere. And so when you multiply through, you get 271 torr. Next conversion, we have to go from 6.6 times 10 to the negative second torr to atmospheres. Okay? So what units go where here? What goes on top? Atmospheres. Very good. Therefore, torr goes on bottom, which allows for those units to cancel. What number goes on top? You say uno? Uno. And what goes on bottom? 760. So then you're going to take 6.6 times 10 to the negative second, essentially multiply by 1, then divide by 760. You get 8.7 times 10 to the negative 5 atmospheres. Let's do a couple that are not in this pack. There's another one that 147.2 kilopascals to torr, and it just follows the same thing. Okay, 1.47.2 kilopascals, and then multiply by the conversion factor. 760 torr goes on top. 101.325 kilopascals goes on bottom. So let's do a couple of examples here. Okay, for part A, it says in countries that use the metric system, atmospheric pressure in weather reports is given in kilopascals. We are to convert a pressure of 745 torr to kilopascals. Okay, so coming into here, and I'm going to dim this a little bit. Can you see that back there? Okay, so first we write what we're given. 745. I'm going to zoom in here. 745 torr And we need to convert it to kilopascals. So what unit goes on top? Not torr. It's what we need. So we get kilopascals. Torr goes on the bottom because we need to eliminate that. And so, again, using that slide with all the conversion units on here, what number goes up on top? 101.325 kilopascals over 760 torr. Now, I want you to take your calculator out and just double check my work. But after I take 745 and multiply it by 101.325, and then I divide it by 760, I should get 99.3 kPa. Get that as well? Okay. Let's look at another problem. The pressure at the center of Hurricane Katrina. Now, quick history lesson. Raise your hand if you remember Hurricane Katrina. Were you, let's see, it was in 2005. You're 1 year old. Colton, I don't think you were. It was a mess. Let me tell you, it was a mess of a situation. Anyway, the pressure at the center of Hurricane Katrina was 902 millibar. Okay. There are 1,000 millibar in 1 bar. So we need to go from millibar to atmospheres. So this is going to require one additional step. We need to go from millibars to bar, and then from bar to atmospheres. Because millibars is not a direct conversion as indicated on that slide. So what we have to do is, just like we do any other time, write what we are given first. 902 millibar. So again, we're going to go from millibar to bar, from bar to atmospheres. That's our plan of attack here. Okay. So again, they tell us the conversion between millibar and bar. Okay. So since we need to go from millibar to bar, what unit's going to be on top? Bar. That means millibar goes on bottom. And then we use the conversion factor that they give us. 1 bar is equal to 1,000 millibars. Then our next step is to go from bar to atmospheres. Okay, so what unit has to go on top? Atmospheres, very good. Bar goes on bottom. Now I want you to tell me what unit has to go on top. What value? Uno. What about the bottom? Very good. Again, the numbers don't change from that slide. Okay? So, again, I want you to check my work. You have 902 millibar. You need to divide it by 1,000. And then take that answer and divide it by 1.01325. And we should get 0.890 atmospheres. Is that good? Now, what does that mean? Okay. Well, in the realm of physics, the faster a fluid, in this case air, the faster it's moving, the lower the pressure. Okay. So 1 atmosphere is normal conditions. Okay, we call that a standard condition. So real quick question is, you can't see what I'm pointing at, is 0.890 greater than or less than 1.0? Less than. So since there is less pressure, and in this case, significantly less pressure in terms of our normal conditions, that means the winds were going extremely fast. So anytime really you start dipping below 9, it's going to be severely significant. 0.9, I should say. And so at one point, Katrina was listed as a category 5, which is really the tipping point of the scales we use to measure hurricane strength. And you're talking about sustained winds, I think it's at one point was over 200 miles an hour. Imagine that. Just the other day, we had winds at, at soccer practice, we were having winds maybe 40 to 45. Multiply that by 5. Pretty big deal, okay? So that's how we use these pressure conversions here. Questions on that? All right. The next thing I want to talk to you about is a manometer. Okay? A manometer is used to measure the difference in pressure between atmospheric pressure and that of a gas within a vessel. So you have this little simple setup here, okay, where you have a container with gas connected to what's called a U-tube, not the video service, okay? And within this tube, we have mercury. This tube right here is open. And so since it's open, it allows for atmospheric pressure, which is this pressure of the atmosphere, to influence the level of mercury. Now I added a little note on here because as you see here, there's a little letter H here, okay? In order for us to calculate the pressure of the gas in here, in this vessel, we have to look at the atmospheric pressure plus the height, or the H, that is here. H is simply the difference between the height on one side to the height on the other of mercury. So measuring from the bottom of this U-tube to this one side, we have 103.8 millimeters. Measuring from the bottom of this tube to the height of the other side of the tube, we have 136.4 millimeters. And so to get the H value, we have to simply subtract these two heights. And what does a manometer use? Well, there's multiple uses for manometers. Here, I just put this little note in there a couple years ago. But it's used to determine and measure the pressure of gases in lab experiments. It's also used in medicine. Have you ever been to the doctor and they put that little black cuff on you and they take your blood pressure? Okay, that device is called a sphygmomanometer. It's real fun to say. The sphygmomanometer. You can also use it in engineering when we're developing aqueducts, even swimming pools. Okay, bridges, anything that could potentially come into contact with pressures, we use manometers. So how do we calculate pressures and the use of manometers? Okay, so I'm going to see if by turning this light off, it's a little easier to see. And if you can't see, come on up. Okay, so on a certain day, a laboratory barometer indicates that the atmospheric pressure is 764.7 torr. A sample of gas is placed in the flask attached to an open-end mercury manometer, much like we saw here. Okay? In fact, this is the image for this particular problem. So a meter stick is used to measure the height of mercury in the two arms of the U-tube. The height of the mercury in an open end arm is 136.4 millimeters, as I said a few moments ago. And the height in the arm in contact with the gas in the flask, right here, is 103.8 millimeters. So first, we need to figure out what is the pressure of the gas in the flask in both atmospheres and kilopascals. So keep in mind these values here. So first thing is we need to figure out what the pressure in the gas vessel is. Okay? So in order to do so, using that formula, P gas is equal to pressure in atmospheres plus H. Okay? You simply take the atmospheric pressure, which they said was 764.7 torr, and add, again, the difference between the two arm lengths. So 136.4 torr minus 103.8 torr. Now, one thing I want to also mention is this. Let's say you have a tube like this. Okay, but in this case, the mercury is higher on the side connected to the gas vessel than it is on the side open to the atmosphere. Okay? This is when, basically what you're going to do for this is when you subtract them, you're always essentially, how do I want to phrase this? You're always going to subtract the right minus the left. Okay? So you're going to subtract the right side value, or sorry, you're going to check the left side value from the right. So when we have situations like this, you're going to end up with a negative value, which will indicate that the pressure in the atmosphere is actually greater than the pressure of the gas in the vessel. Okay? So again, for our image here, it's the right minus the left. 136 is the right, minus 103.8 is the left. The right side minus left side. So when we solve for this, we find that the pressure of the gas is 797.3 torr. So we've got that. The first part of our problem says we need to solve it for atmospheres. So we take our 797.3 torr, use our conversion factor of 1 atmosphere over 760 torr. Torrs cancel. We get 1.049 atmospheres. So right off the bat, that tells us that the pressure in the gas is greater than the atmospheric pressure. That's greater than 1. The other part says we need to go from our units to kilopascals. And you can do this a couple different ways. You can use the same answer you just calculated, or you can go back and use the answer you initially calculated. Doesn't matter. Okay, so we'll go ahead and use the 1.049 atmosphere and solve for kilopascals, where we have 101.325 kPa over 1 atmosphere. Atmosphere cancels out, and we get 106.3 kPa. Okay, so we're going to do, probably before your first quiz, another example of a manometer problem, okay? So we'll see this again. But what I want you to do next is this. I want you to take a few minutes and do the practice exercise. You have two parts. You need to go from 0.975 atmospheres to pascals, and then 0.975 atmospheres to kilopascals. Take a few moments, and then we'll go over it together. So just a quick check. This is what we should have for our answers. For A, going from atmospheres to pascals. Again, the conversion factor is 1.01325 times 10 to the fifth. That's a 5. You can't read my chicken scratch. Pascals is equal to 1 atmospheres. You should get 9.88 times 10 to the fourth pascals. Again, since we're using scientific notation with powers of 10, you need to use parentheses. For B, atmospheres to kilopascals, again, its conversion factor is 101.325 kilopascals is equal to 1 atmosphere. Again, the atmospheres cancel out, and we should get 98.8 kilopascals. We do a lot of conversions in this chapter, so just so you know. So it's going to become like second nature to you.